until I figure out how to upload these. All right, so if you have your student workbook, that's what we're going to do all semester. We're going to follow along in these, and today we're going to cover all the chapter 1 basic, organic material, and yeah, it should be pretty easy today. So let's just get started. So here we are. So the first concept is functional groups. So what functional groups are, it's really easy. It's kind of just identifying what they look like on paper. So what a functional group is, and this is kind of important to talk about right now, is it's a specific series of atoms in a specific connectivity that possesses a specific reactivity. Okay, so it's a specific connectivity of all these atoms that possess a specific reactivity. So starting in chapter 6, each of these functional groups, like a nitro or an epoxide or an alkene, is going to get its own chapter. And if it gets its own chapter, then that means that we're going to look at all the different reactions that can happen with that one functional group. So chapter 6 is actually alkenes. So a whole chapter is dedicated to alkene reactivity. And chapter, I think, 11 is going to be ketones. So you'll deal with a whole chapter on ketone reactivity. Okay, so let's get started. So you have a front cover of your textbook. I think it's also scanned to the Canvas page. There's about I think 20 functional groups that you should be able to identify. So for starters, let's go left to right. We see that we have a nitrogen in between 2 carbon atoms. That's an amine. Okay, so this would be an amine. Okay, and we're not classifying yet. So if you're asking to classify, just hold on. You'll see me on the next page. Just making sure everybody's in here. Yep, so that's an amine. Okay, so these carbon-oxygen-carbon bond would be an ether, okay? And I have a nice way to remember ether. Ether looks like an Ethernet cable. I don't know if you guys know what that is. It's plugging, the hardwired internet into the wall. So I don't know, it kind of looks like a socket in the wall and the carbon chain is plugging it in. So ether, I don't know, that's how I did it. A carbon-nitrogen triple bond, that's a nitrile group, and that kind of makes sense because it has a nitrogen and it looks like an I, like nitrile. So that helps you. That's a nitrile, or sometimes called cyano. Could be either one, nitrile or cyano. This carbon ring, more specifically this alternating double bond, single bond pattern, is called a benzene ring, okay? Benzene, or sometimes called arene, whatever you want to call it, benzene or arene. Listen to me right now. If you ever see a benzene, do not do any chemistry with it until organic 2. Okay, so it's very, very common for people to make mistakes with benzene, this specific structure later on in other chapters, but you really don't even talk about benzene until Orgo 2. So you should never, ever play with benzene in organic 1, just for now. All right, so here we have that kind of same carbon-nitrogen-carbon pattern, but we have this extra carbon-oxygen double bond, that's a carbonyl. So together, this would be an amide. So notice the difference between amine, M-I-N-E, versus amide, M-I-D-E, okay? Amide has this extra carbonyl, okay? And this final terminal functional group is going to be an aldehyde, okay? And we have to distinguish between aldehyde and ketone. So ketone is going to be in the middle of some sort of molecule, while aldehyde is terminal, always terminal. So maybe I'll write that for you guys. Aldehydes are different from ketones in that they're always terminal, okay? Always towards the end. All right, so you kind of see this isn't so hard. Just be able to know your 20 functional groups. It's easy points on your first exam. We'll do another example real quick for B, and then we can jump to the next topic. So from left to right, we have this carbonyl again, this carbon-oxygen double bond, but now we have this kind of adjacent hydroxyl group, this OH group. So this would be a carboxylic acid. So a lot of you guys probably have recognized this in other science classes, probably Bio 1. Carboxylic acid, okay, and it's acidic with that proton we'll see in chapter 4 coming up. Okay, so this functional group, this carbon, oxygen, hydrogen, connectivity is an alcohol, okay? So there are technically the organic definition of alcohol is ROH, or carbon OH. So the alcohol you drink is that, ethanol, okay? This is ethanol. And what makes it an alcohol is this carbon group, COH. Okay, so that's the alcohol. Okay, just fun fact, ethanol. All right, so this group right here with the hydroxyl group on the benzene isn't just benzene now, it's called phenol. Okay, P-H-E-N-O-L, so phenol. Okay, so benzene, there's a lot of different names. There's benzene, there's arene, there's also phenol. We don't really do phenol, okay? So don't worry about phenol, but that's where phenol comes from, if you guys can see that. It's a combination of phenol plus alcohol makes phenol. I just kind of like to prove it to you guys so you know, it's easier. And over here, we have another one of those amides. Okay. Here, this carbon-carbon double bond is an alkene. And finally, over here at this end, we have an NO2 group, and that is nitro. Okay, so nitro is not nitrile. Okay, so nitro. All right, and I just want to tell you this right now. This is something you need to commit to memory. Okay, so this is what a nitro group looks like, the Lewis structure. It's really important. It doesn't seem important, but it really comes up a lot in Organic 1, like low key. So just make sure you commit this thing to memory. So the nitro group, NO2, looks like this. N double bonded O with N single bonded O. There's a positive and a negative charge. Definitely worth knowing that. All right. You guys see this? This is pretty easy. Does anybody have any like issues with this? All right, does anybody have any issues with this so far? You can put in the comment box or just say it out loud, whatever.
For the alcohol groups, are they always going to be like pointing outwards or inwards, or could they just be like a single bond?
They could be, yeah, they could be planar. So they could either be like a wedge, a dash, they could just be like a line, as long as it's carbon, oxygen, hydrogen in order. Then it's
Gotcha, thank you.
Yeah, of course. All right, anybody else, or we're good so far?
I have a question.
Sure.
So we need to know like all the functional groups from the document and like anything she mentions in this workbook that's not on there too, or?
So I don't know, are there stuff missing in this, or are there extra things in this workbook that you don't see in the textbook?
Yeah, I think so. Just like, I don't think phenol's like on that like PDF.
Okay. Yeah, so pretty much everything on that inside cover you need to know, and anything we cover here is also going to be on there as well. Yeah, so she would expect you to know phenol as well. Okay.
Okay, cool. Thank you.
I think we got some comments in the text. When drawing resonance for nitro, should we do resonance for each option, or is it irrelevant? We're going to get there. I'm going to do an example of nitro later, so just hang on. All right, anybody else with functional groups? I just want to comment, this one is going to be thiol, okay? This one is going to be Ester. I like this one because Ester is kind of like an older person name, so it looks like glasses with the 2 oxygens. So whenever I see this, I think Ester, glasses. I don't know. Maybe that helped you guys. Okay, and then one more thing I want to talk about down here is this group is the Lewis structure of a nitro. So we talked about that. This is why it's important to know that. This is nitro. And then over here, this weird, crazy guy is an acid anhydride. I'm just trying to get all of those for you guys, acid anhydride. And I think you guys know the other ones by now. Okay, so that's it for functional groups. It's an easy like 10 points on your test. So, you know, just know them, not too bad. Okay, we're gonna move on to classifying. I know I didn't cover all the functional groups, but you know, I think it's pretty self-explanatory. So the next thing is classification. So you can classify a lot of functional groups, but the only thing we're going to require you to know is the alcohol and amine classifications. So I used to have this phrase like a long time ago when I first started was alcohols leave you hungover and amines are mean, so don't forget to classify them. Like I said again. So alcohols leave you hungover and amines are mean, so don't forget to classify them. I know it's a weird phrase, but like you'll think about it when you're taking your test and you'll remember. I have a question here. Is the benzene attached to another ring still a benzene in number 8? Was that on the last page?
Yeah, sorry. I don't know if it was number 8. It was on the last page, but it was like a benzene. I think it was a D. Like it's detailed like attached to the other ring.
Yeah, great question. It's still a benzene. It's still a benzene.
Okay.
Yeah. And then this would be an ether. Okay, so that would be an ether next to the benzene. But yeah, good question. All right, so, and you guys can like do your audio, do your what is it called, the camera if you guys want to, whatever you guys feel comfortable with. Like it's really casual, like no pressure. All right, so when we're classifying amines, we classify it based on how many carbons are directly attached, okay, to the nitrogen. And that's a little bit different from alcohol. So let's just do the amines first. So over here, we have this amine functional group. And how many carbons are next door? So there's 1, 2, 3. So this is a tertiary amine. No thinking, okay? Over here, we see we have 1, 2, and that would be a secondary amine. Okay, and you guys are kind of getting me. Over here, we have 1, 2, 3. So this would be a tertiary amine. Okay. Same thing here, 1, 2, 3. This would be a tertiary amine. And down here, we only have 1 carbon group, so this would be a primary amine. Okay, so I think that's pretty easy so far. Does anyone have any issues with classifying amines? It's just then look for the number of carbons directly attached to your nitrogen atom. Okay, pretty easy. All right, alcohols are a little different. So like I said before, I said ROH or carbon OH, that was the functional group. I say that for a reason. So the alcohol isn't just the OH. The alcohol is actually the carbon that is attached to the OH. So in theory, it really should be circled this with that carbon. That is the whole functional group. So ROH. So we look to see what carbons are attached to that main carbon on the alcohol. So over here, we see that there's 1 carbon attached, 2 carbons attached to that main carbon of the alcohol. So this would be a secondary alcohol. Okay, so it's a little bit different than amines. So then for this guy, it would be, this is the main carbon of my alcohol right here, where I put that dot. And how many carbons are attached to this one? Well, 1, 2, and 3. So this would be a tertiary alcohol. Okay. And then over here, this is the main carbon of the functional group. And then there's 1 attached. So this would be a primary alcohol. All right. Anybody like confused on any of these things so far? So amines and alcohols are a little bit different, but once you get them, they're super easy to classify. You'll just be able to see it on paper and you'll know that's tertiary, that's secondary. You don't even have to count. Okay, I think it's pretty good. Let me see anything down here. Yeah, so let's just do, this one would be 1 group, 2 groups. So this one is just going to be a secondary alcohol. And I'm just jumping around. Down here, we would have, this is the main carbon of the alcohol, and then there's 1 carbon attached. So this is definitely a primary alcohol. And yeah, I think that's good enough practice with that. Any questions? All right, I think we got something in the chat box. Okay, you have to, that's a great question. Everybody look at this question in the chat box. It was sometimes when you see functional groups, you kind of see parts of it, like for an example, amide. So let me just draw something. This would be, it would be wrong to say amine and ketone. That would be totally incorrect on the test. You have to recognize the bigger, larger, more macroscopic function group, and this would be an amide overall. Okay. Any other side group classifications? Leah, what do you mean by that? You want to elaborate? Do you mean like more than primary and secondary, or more than an alcohol and an amine? Let me know when you figure that one out. More than an alcohol. Okay, great. No, you only have to, for this test, have to classify alcohols and amines. Yes, there are other ways to classify, like alkyl halides. You can classify those in other ways, but for where you guys are at right now and for your exam 1, only alcohols and amines. And this is why this workbook's set up this way. This is pretty much like everything that you need to know for your exam as we go by. Okay. Let's move on to hybridization. So I always take, yeah, no problem. I always take a little bit of a detour. Does anybody have a question? No? Okay. So I always take a little detour when I explain hybridization because I like to go into the theory real quick. So this is where if you have extra paper, let's take that out and you can just copy these notes down. I kind of like to condense Dr. Peterson's notes even more than your current notes so that you guys can look at something really quickly and be like, yeah, I got it. I know what this is. Okay, so hybridization. So what is this? What is this weird concept? And a lot of the times you've seen it in Gen Chem before and you were like, what the hell is this? This is so confusing. I have no idea what hybridization is. I'm just memorizing it. But I'm gonna teach it to you where you guys understand it. There's no memorization. If you are memorizing this, it's because you don't know something. So speak up if you're finding yourself memorizing it, okay? You guys should all leave here like understanding the theory very well. All right, so let's start with something like carbon, okay? And back to Gen Chem. I hope it clears up. Back to Gen Chem, if you guys remember. Let me see if I can get a different paper. Okay, so hybridization. So back to Gen Chem. If I were to ask you, what is the electron configuration of carbon? You would say 1s squared, 2s squared, and I believe 2p2. That's from memory, I don't really know. So 1s squared, 2s squared, 2p2. If somebody wants to fact check me, that'd be great. But we wrote that, and you know, that was all great. And we basically knew at the time that there were one s orbital, you know, that was a core shell, and it has 2 electrons in it. And then higher than that, there's going to be a valence s orbital and a valence p orbital, and each of those have 2 electrons respectively. But you know, which one is involved in forming bonds? Like you can clearly see we have, thank you, Roxana. And clearly you can see that we have all these bonds now. So which orbital? Is it the 1s squared? Is it the 2s squared? Is it the 2p2? Which one is involved in bonding? Okay? And that's a kind of like big question here. And the answer is all of them. And that's why the term hybridization exists. Hybridization just means that you are hybridizing or morphing together all of these orbitals to form hybrid orbitals, okay? So we can call these atomic orbitals, and these are hybrid orbitals, okay? So atomic, so that makes sense. For the single atom in the single elemental state, we're gonna have these 1s squared, 2s squared, 2p2 orbitals. But in an actual molecule, we don't have those atomic orbitals anymore. We have these hybrid orbitals, okay? So this is what's used in bonding, hybrid orbitals. I'm just writing these little facts for you. Used in bonding, a blend of everything that you see, okay? So we're gonna basically go into 3 different molecules, okay? So we're gonna talk about methane, methene, and ethine, and that should hopefully like get you guys clear on these examples. So example 1, so this is going to be sp3. So this is our first one we're gonna talk about, sp3, all right? So in sp3, we're gonna have a molecule like methane, okay? And I'm gonna draw that Lewis structure for you. So here, here, and here. Okay, this is the Lewis structure, okay? And I don't think you guys know what wedges and dashes are yet, but what this means is this H is literally coming off of the paper and into my face, and then that dash means it's going through the paper and like into the desk, into the table, okay? And that's the 3D geometry. So wedge coming out at you, dash going into you, and those lines just mean in plane, so quite literally in plane with the paper, okay? Kind of imagine that. Looks like a seesaw, if you can imagine that. It's like a seesaw. Okay, so what does this mean? Well, if I were to draw, you know, this energy plot, and this is really important. I don't know if you guys saw my YouTube videos. So we had this orbital and we have these orbitals, okay? And this would be the 2s orbital, and this would be the 2p's orbitals. And all I'm doing is qualitatively showing that the p is a little bit higher in energy than the s. And then the 1s would be all the way down here, but we don't care about the 1s. All we care about is our valence electrons, which would be the 2s squared and the 2p2, okay? So only valence, so maybe I'll write that here. Valence, I guess, atomic orbitals. Okay, those are the most important, valence atomic orbitals. Okay, so let's populate those. So according to my electron configuration that I drew up here, we see that in our 2s orbital, we have 2 electrons. So let's populate that. Okay, and then in the 2p orbital, I have 2 electrons as well. So let's follow Hund's rule. Okay, and you know, make sure that you fill these in correctly. Okay, so then what happens in this specific bonding? Well, what happens is all 4 of these atomic orbitals, all 4, so the 2s, the 2p, and we'll call this maybe the 2px, the 2py, the 2pz, remember they're all, and when you drew, I don't know if you guys remember this, and maybe it was like kind of counterintuitive back then, but remember it was like draw these boxes, and it was like, this is the 1s, and then you drew these boxes maybe, and this was the 2p, and then maybe like 3D, you drew 5. Do you guys remember that? If you do, like, this is the reason. There's really 3 types of p orbitals: pxy, px, pz. So, you know, that's why you draw 3 lines, if anyone cares. It's always 1 line for an s, 3 lines for a p, 5 lines for a d, 7 lines for an f, but we're not going to get beyond s and p, okay? So that's just a side. But in all intents and purposes, all of these orbitals are going to come together to make 4 equally degenerate, so degenerate just means the same energy, hybrid orbitals. Okay, does that make sense? So all we did was we took all 4 of these orbitals, all 4 of these atomic orbitals, and mushed them together. Okay, and there's this rule that a lot, I don't know if any of you guys are chem majors, but there's this big rule that a lot of chem majors have to follow is what goes in, what comes out. Okay, so if there are 4 in, we need to get 4 out. Okay, maybe that helps you. 4 in, 4 out. So in this situation, the 2s, the 2px, the 2py, the 2pz all come together to make these 4 sp3 orbitals. Okay, so what does that look like? So let me take this same methane structure and now let me draw for you. So this would be, okay, so what these kind of lobular structures are, these are the sp3 orbitals. These are the hybrid orbitals, okay? sp3, 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 okay? So what happens is that as this atom, this let's just say it's a single carbon at this point, a single carbon atom, as it approaches other atoms, it hybridizes from this atomic structure to this molecular structure, all right? Are we kind of following that so far? Somebody want to just say yes or something? You know we're good? Good, okay, we're following. All right, so we have all 4 of these sp3 orbitals, and what happens is that they're gonna overlap with these hydrogen. So these hydrogen 1s orbitals, these hydrogen 1s orbitals. And that's literally what a bond is. All that a bond is in organic chemistry is when orbitals overlap and touch each other. That's a bond, that's it. Okay, so why, maybe somebody wants to put in the chat box, why is it that hydrogen is only 1s? Why didn't I show like sp3 or sp2 or sp? Does anybody have a good guess? Why is hydrogen just 1s on this diagram? Okay. Perfect, Hal, that's awesome. So literally hydrogen, if you rewrite the electron configuration back up here, like let's say I was gonna do this for hydrogen, you just write 1s1. So there's literally only 1 atomic orbital. So I can't even hybridize. It's not even possible to hybridize because I don't have extra ones to do so with, okay? Great guess. I mean, that means you guys get it so far. All right, so that's the sp3 configuration, okay? So this is all you need to know, all right? So it's going to be typically with 4 electron groups. So you can see that there are 4 bonds, okay? So typically 4 main bonds. And these 4 atomic orbitals come in to hybridize to form 4 atomic orbitals out. Okay, and just some facts to know, there's always 109.5 degree geometry, and it's also known as tetrahedral. Okay, those are the 2 things you need to know. Okay, I know my notes are all over the place, but kind of just give you it real quick. So anytime you see an sp3 center or an sp3 structure, it's always 109.5 electron geometry and always tetrahedral. Always, 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 always. Okay, so that's sp3. I'm going to keep kidding you guys with sp2 and sp, so if you're a little confused, don't worry, I'm going to catch you. All right, so let's try sp2. And does anybody have any questions so far while I'm writing this out? All right, good. So sp2. So what sp2 is, an example is ethene. Okay, ethene. Okay, so ethene looks like this. And this is the Lewis structure. Question in the chat box, a couple of them. Let's see. Yes, Caroline, we are going to talk about that when we get into the problems right after I finish doing the concept. Yes, that is such a great point. Yeah. So if anybody wants to see what Caroline's talking about, the electron geometry is not the same as molecular geometry. It's not, and we're going to talk about that in the next example. But thank you. Okay, so this is ethene. Okay, so we have that same electron. Let's just do that same electron energy diagram. So you guys understand this at this point, 2px, 2py, 2pz. Okay, and there's something different here, okay? So when we have this double bond, okay, it's known as sp2, and why is that? Well, what happens is instead of all 4 atomic orbitals coming together and hybridizing, only 3, okay, are gonna do so, okay? So that's kind of weird. Why would 3 only do it? So I'm gonna circle these and say these are gonna hybridize. So I'm gonna write the word hybridize. And I'll write the new energy plot down here. And the new energy plot is going to be this. Okay. Does that kind of make sense so far? So remember, I said that rule is what goes in, what comes out, okay? So if I'm putting 3 atomic orbitals in to hybridize, then 3 are definitely gonna come out. And I didn't play with that 2pz. That 2pz is just kind of like hanging out. It's kind of like when you were back in Gen Chem and you were dealing with spectator ions. You wrote them, but they never really did anything. And that's kind of what we're doing here. What's hybridizing are these 3, okay? And that's all you need to know. So that's why I get sp2. And something I failed to talk about just before, one more thing real quick, is why is it sp3? Where does this name come from? Well, if you look at your powers, S1P3 is really what it is. What's 1 plus 3? That's 4. Well, how many orbitals did you have come in? Mind blown. 4 in. Do you guys follow that? So if your powers, that's where this name comes from, sp3. It's such a weird name. Well, 1 s orbital and 3 p orbitals come together and hybridize. Okay? That's the name. Whoa, cool. I don't know. All right, let's keep going. So over here, what did I just talk about? Well, instead of 4, only 3. So that means 1 s and 2 p's come together. sp2. Boom. Cool. I don't know if you guys are having an aha moment, but so that's that. Anyway, so how does this look in terms of like that diagram again? What does this mean? So let me fill in these electrons just so you guys know. Same thing here, and then 1, 2, 3, and 4. Okay. So we're here. And what does this really look like in terms of bonding? Well, for this carbon, we're going to have this one, and for this one, and this one. And for this carbon, we're going to have that. I'm going to explain this in a second. Okay, so I'll give you guys a second to draw that out. So all I'm doing is drawing these kind of like petals, I guess they look like. And why do I draw it like this? Well, the circle means like the sphere, you know, s orbitals are spheres. And this kind of like petal looking thing is the p portion or the lobe, you know, they're dumbbells for p orbitals. So this drawing, this kind of like circle and this lobe is the 2D drawing for what a hybrid orbital looks like. It's to denote that there's S and P mixes in there, okay? You guys are curious. So basically what I drew are all the sigma bonds, okay? So all the sigma bonds. And all the sigma bonds always form from hybrid orbitals. So that is definitely worth knowing right now. All sigma bonds come from hybrid orbitals. That's really important. Okay, so remember, sigma bonds are the single bonds. So this single bond, this single bond, this single bond, this single bond, and then one of these bonds in here are all going to be created via hybrid orbitals overlapping. Okay, so let me just bring in my hydrogens just so we can just ignore those. The hydrogen 1s's are here, the hydrogen 1s's are here, the hydrogen 1s's are here. Okay, so we have done everything that we necessarily know at this point. We know that there are 3 sp2 orbitals, hybrid orbitals, for each carbon atom, and that's the 1, the 2, the 3, and the 1, the 2, the 3. Okay, for each one, there is going to be 3 hybrid orbitals. So then what happens with this extra pz? Like what's going on there? Okay, so I'm going to draw it like this. You know, p's are lobes, like dumbbells, whatever. And this is the unhybridized p orbital. Unhybridized p orbital. Okay? So these unhybridized p orbitals each have 1 electron, right? It's 1 electron. Okay. So what happens is because I have these 1 electron in one unhybridized p orbital, and then 1 electron in the other unhybridized p orbital, those orbitals will overlap, and that forms that pi bond. Okay? So now you guys can see this kind of orbital depiction. We have this, what is it called? We have this sigma bond right here, and then we have this extra bond on top of it. That's the pi bond, okay? So you can see we have sigma, 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 and then this is our pi bond, okay? So pi bonds always, all pi bonds come from unhybridized p orbitals. P orbitals. I hope you guys can read that. I'm writing it really fast. Okay, so you guys are kind of following, right? So it seems like the less amount of hybridization I have, so like the less amount of atomic orbitals I'm using, the more capable I am of, forming these pi bonds, these double and triple bonds. All right. Does anybody have any other questions on sp2? Okay.
I have a question really
Sure.
quick. So you know how we're just taking, sp2 is just taking 3 orbitals, and then the other p orbitals left for the pi bond.
Correct.
But after we hybridize them, so like when you circled just one of the two s's and then two of the two p's, those electrons don't only stay in those 3, like they would go to all of them. You know what I mean? Like you circled it.
What's the all 3? You're talking about the sigma bonds?
In the energy diagram that you drew.
Oh,
so
okay. This?
the one above it. So you circled, yeah, you circled the ones that are going to hybridize.
Correct.
But the electrons still are like, we fill them into all of them, like even the 2p one that we didn't use.
Oh, are you? Oh, okay. I get what you're saying. So,
Yeah.
so I basically could have. You're right. I should have basically showed you this. Does that seem better for you?
Yeah, but why?
Because one electron is always going to stay in the p orbital, and that has to do just because it is larger than the other ones. Like all these hybrid orbitals and the 1s are very tiny and compact, but these p orbitals are a lot bigger. You don't really need to know this. This is like a little bit more in detail for orgo, but there's always one left over in the p. I don't want to like confuse you too much with the knowledge, if that makes sense. But you're always going to have however many orbitals are going in. So let's say there are 3. Each one of those will always have 1 electron. Same thing for the sp3. So there were 4 going in, so each one of those hybrid ones will have 1 electron. And you'll see for sp the same type of trend. All right. Anybody else? Yeah. All right. I think you guys are getting me. So sp, the last one. I know this is detailed, but I think it helps a lot of you guys. Ethine. Okay. So we did methane, ethene, and ethine. So ethine looks like this. I think some of you guys can already see where I'm going with this. So this is ethine, okay? It's very flammable, just so you know. What else? And very basic, no, very acidic. What's the other thing? So we want to draw the energy plot again, okay? And we have the 2s down here, and then we have the 2p, x, 2py, 2pz. Okay, so if it's sp, s1p1, what do we think? Well, instead of 4 or 3, we're only going to mix 2. Boom. So let's just do these 2. So 1, 2, 1, 2, right? Yeah, 4. Okay, so then those 2 are going to hybridize together. And then you get sp, and then 2py, 2pz, and I'll move that over. 2py, 2pz, 1, 2, 3, 4. All right, so that is all that happened. And in this case, we have an S and a P, so that's why it's SP. There's only those 2 mixing happening here. Okay, so let's draw that kind of orbital framework again. So if I were to draw the sigma bonds, what are these sigma bonds? These are going to be atomic or hybrid orbitals. Somebody put in the chat box, somebody. What am I drawing? These are the sigma bonds, which are the hybrid orbitals. Yep, hybrid orbitals, great, 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 which also correspond to the word sp. Okay, so sp and hybrid is what I'm drawing right here. Okay, the hydrogen 1s would be here. The hydrogen 1s would be here. So these are the carbon-hydrogen bonds that we see up there. Okay, and this is the sigma bond. Okay, so the carbon sp with another carbon sp overlapping. So then what about those 2 extra pi bonds? Well, thank goodness I have these 2py's and 2pz's going on. So let me draw, maybe this would be the, let's call that 2py. Let's call that one 2py. Okay, and each one of those has 1 electron. So let's draw the connection there. So you can see that's one of the pi bonds. And then each one of those carbons also has an unhybridized 2pz. So maybe I'll draw it here in like a different orientation. Let me draw it down here. Okay, so now you can see there are a total of 3 lines, 3 kind of like squigglies in between. And those are the 3 bonds that you have in between the carbons, okay? So I hope that kind of like gives you a little bit more clarity into what hybridization is. This is all you really need to know. I just forgot to say one more thing about these 2 things. sp2, like we said before, instead of it being tetrahedral, it's trigonal planar always, trigonal planar electron geometry always, and 120-degree bond angle always. Okay, so that's what you need to know for sp2. And then for sp, you need to know that it's always linear electron geometry and 180 degrees. Okay, so I'm going to show you these again. If you guys want to take like a screenshot, I don't really know how you guys can do that on Zoom, but this would be the first guy, remember, and I can move it up. So this was the sp3, remember, so we had all the 4 coming together, 4 coming out. Recapping, it's 109.5 electron geometry, and then tetrahedral electron geometry as well. Here's what that structure looks like. Cool. All right, sp2, instead of 4, it's going to be 3 of them. We talked about what that unhybridized p orbital means, and it means that it's capable of forming these pi bonds, okay? And all sigma bonds are always going to be from those hybrid orbitals. All pi bonds always form from the leftover unhybridized p orbitals. And that was trigonal planar in 120. And then ethine, last and not least over here, we had those two unhybridized p orbitals left over to form those 2 pi bonds, and that was linear in 180. All right, got some questions going on. Brian, when you say like 4 and 4, are you talking about electrons or orbitals? I'm talking about orbitals, honestly, but it also kind of works for the electrons. I'm talking just about orbitals. So when I say like these, when I circle right here, when you see on the screen, those 2 orbitals, those 2 atomic orbitals are going in. So I'm expecting 2 hybrid orbitals out. So earlier with this one, I saw 3 atomic orbitals in, 3 hybrid orbitals out. That's all I'm talking about. Atomic orbitals in, hybrid orbitals out. That's it. So before it was 4 atomic orbitals in, then it's 4 hybrid orbitals out. Like that. Perfect. All right, that's enough theory. I hope that clarified some things. Let's jump into questions. All right, so now hopefully you guys will like get this a lot more when you guys are doing this. All right, so we can just look through this example real quick, and we're going to see that for A, we're looking at this carbon nitrogen, or we're specifically looking at this carbon in the carbon nitrogen triple bond. Okay, and that carbon has, you know, this triple bond next door, but if you didn't know that a triple bond was sp, what you can do is you can just circle the areas of electron density. So here we can see around that carbon there was a triple bond and a single bond. So how many areas is that? That's 2 areas. So if it's 2 areas, your powers have to add up to 2. So S1 P1. So this would be an SP center. This is a shortcut. There's no like real logic to the 1 and counting the areas of electron density. I'm just like giving you a shortcut to always get it right. Okay. We now know the theory. This is just to get the questions right. All right. So SP. So then you know, based on memory, that SP is always 180 and always linear. So if it asks you what your bond angle is, you're going to say 180 like they did right here. Okay. But in this case, we're looking into the molecular geometry being the same as the electron geometry, but they're not the same. So what I want to talk about real quick up here is that electron geometry equals hybridization. So one of those hybridization words that I told you. So like tetrahedral, trigonal planar, or linear. Those are the only three electron geometry configurations you can have. What molecular geometry is, that one is going to be valence shell electron pair propulsion theory. I bet you there's a whole bunch of eye rolls right now. We don't teach you Vesper theory. We assume that you know that coming in from Gen Chem. So make sure you guys go over those structures, meaning AX2 is, you know, linear, AX2E is bent, AX4 tetrahedral, AX6 is octahedral, all those things again, okay, they come up. So I'm sorry, it's the only thing for this test that you have to like kind of go over your old material. All right, so in this case, what we're seeing is we have AX2, if you remember what that is, and that would be linear. Okay. Somebody have a question? No? Okay. Yeah, okay, so that was A. So for B, we see that we have, okay, we're counting areas of electron density. Okay, so there's 1 area, 2 areas, this lone pair counts as 1, and that lone pair counts as 1. So I circled 4 things. So 4 things, my powers, S1, P3, 1 plus 3 is 4, okay? So B, that atom, is sp3. Bond angle I know is always 109.5. How do I know it's bent? Remember, it's tetrahedral electron geometry, but we wrote bent here. It's bent because this is AX2E2. Okay, that's bent. Okay, that's why it's bent. C, okay, so for C, we're going to count areas of electron density. Okay, so what we have here is we have, I guess, a single bond here, 1, another single bond, 2, a single bond, 3, and the lone pair, 4. Okay, so that's 4 areas, and I would think sp3, but I don't have sp3 for some reason written on C. Why don't I have sp3? Well, the reason is there's resonance, okay, and we haven't really talked about resonance yet, but we're going to start to talk about it now, where whenever you see resonance possible, you have to draw the other resonance structure, the lower resonance structure. So what I mean by that is I'm resonating these lone pairs in here to form a double bond, a nitrogen and carbon double bond. And then that forces these electrons to go up because we exceed the octet there. So this is kind of what we're looking at. And I'm just gonna, this is R for the rest of the molecule and R for the rest of the molecule. So all I did was reproduce this amide below here, but with the resonance form, meaning that lone pair forcing in to form a double bond and then forcing those bonded electrons out, okay? We're gonna talk more about resonance. I know if you don't really get this right now, don't worry. Kind of all these concepts in the beginning kind of overlap, so it's a little, sometimes, you know, you gotta give and take with these things. But anyway, after I resonated, now I count the areas of electron density. So I see I have 1 sigma bond, another sigma bond, and then 1 triple bond. It doesn't matter that it's a triple bond. It doesn't matter that it's a double bond. It doesn't matter. It counts as 1 area of electron density. So overall, we have 3 circles. So that's sp2. That's why I see sp2, okay? And that's that, sp2, 120. And it's bent because I have, what is it, AX2, AX, is that bent? I don't think this is supposed to be bent. What does it say in your workbook? Does it say bent for you guys?
Trigonal planar.
Yeah. So I printed out the original copy on accident today. So I knew there'd be some errors in here. So that should be trigonal planar. I'm sorry about that. All right, anybody have any questions? Any more questions on this stuff? Okay, and then we're gonna go to the next example. Cool. All right, let's do it. So over here, we're gonna, sure.
What did you mean by going to the lowest resonance structure?
Okay, so yeah, I'm not the best with English. That's one thing. So I tend to like stutter and say some things weird. So just call me out if I do. By lower resonance structure, I meant lower hybridization scheme. So here we saw that we thought it was sp3 because we saw 3 bonds and 1 lone pair. So that was 4 total areas. We thought it was sp3, but the lower hybridization scheme is this sp2 guy. That's what I meant by that.
Thank you.
Yeah. Mm-hmm. Okay, so let's talk about this for a second. So for A, count areas of electron density. So we have a lone pair, a sulfur hydrogen bond, and a sulfur carbon bond. So that's 4 total areas. 1, 2, 3, 4. 4 areas means my powers have to add up to 4. S1P3, so that would be sp3, okay? What is that bond angle? Well, we have that committed to memory. It's 3 numbers, 109.5 degrees, okay? And the electron geometry would be tetrahedral, but my molecular geometry follows the Vesper theory. So there would be 2 bonds, so that's AX2, and then 2 lone pairs, E2. And if you guys remember that one, that would be bent. Okay, I think we got some more questions coming on. So we use the lowest hybridization possible for the resonance. Yes, we do. If they give the other way around, then we would still do the resonance and still decide sp2 is right. Yes, you always just want to get to the lowest possible one. Yes. Okay. All right, you'll see that with B. All right, so for B, there are 2 lone pairs on oxygen, and right now it looks like sp3. All right, so this is a perfect example of what you would be doing on a test. You would see sp3, you would think right here, but there is resonance possible with that carbonyl. So I'm just going to draw that form over here. I'll draw those arrows in. Okay, so the resulting structure should be that, and R just means the rest of the molecule. Okay, so you can see what happens after I resonate. So then, if we count the areas of electron density, we have a pi bond, a single bond, and a lone pair. That's 3 total areas. So B is really sp2, not sp3. Okay, and sp2 corresponds to 120, like we said. And then if we do the formula, AX2E, that would be bent as well. Anybody having any issues with this? I think it's pretty easy once you understand like the theory and stuff like that. Is it because there's a near, Correct. Yeah. So when we talk about, I don't even know how much time I have left. We're coming close, so hopefully I get there. But when we get to the resonance stuff, you'll see we're going to look for specific, things in a molecule, and of those, they would have to be double bonds or triple bonds nearby. And you're right to think that since we don't have those there, we're not doing resonance for that thiol group. Yeah. Good job. Good question. Okay, so for C, we're already in a resonance. We're already in a lower configuration, meaning we're already sp2, so we don't really see lower than that. So we have this single bond, this sigma bond, and that triple bond around. So that would be 3 areas. So that would be S1, P2, so that's sp2. And that would be 120 degrees. And this is going to be AX3 because I see 3 bonds. So AX3 is trigonal planar. So sometimes your electron geometry matches molecular, sometimes it doesn't, whatever. All right, I think that's enough practice for this. So I just want to do D real quick. So it was changed to cyano in your book. I had it as nitro before. So CN, what is CN? Well, CN, if I draw it out, is actually this, okay? And we're pointing to the carbon in that. So this would be what D was, that carbon in the cyano. And we see that we have this single bond, and we see that we have that triple bond. So it would be SP. And SP was always 180. And, we see 2 bonds, so that's AX2, and that was always a linear structure. And that's how I always get these. All right. It wasn't supposed to be nitro. It's corrected as cyano, I think, in your book. And yeah, that's how I do those. Anybody have any question on hybridization, difference between electron and molecular, bond angles, anything? Okay.
So for C, or problem C, letter C, would that
be letter C, right here?
Yeah.
Okay.
Would that be would that be SP2?
Exactly. Yeah. Why would it be SP2? Tell everybody.
Because there's lone pairs on nitrogen, but then there's also that double bond, right?
Yep. Perfect. Yep, you got it. That's exactly what it is. Because there's that lone pair and this pi bond next door, which we'll talk about when we get to resonance, it's a very, very obvious sign. You're going to resonate and you're going to take the lower hybridization scheme. So you got it. Yeah.
All right. Thank you.
Mm-hmm. Anybody else confused on that? That's very important with these questions. It's like the big trick on your first exam, knowing to resonate versus not resonate.
For D, what you just did with the cyano, would there be resonance between the C and the N? Like would the triple bond go to the N?
You could technically resonate out, like take that pi bond out and put a lone pair. That's not good. Don't do that. Yeah. We'll talk about it when we get to resonance of why. The problem is you get two formal charges, and one of the rules for resonance is you want to minimize those formal charges. So we'll talk about it. Yeah. Okay. So I'm trying to move a little bit faster because we're going a little slow today. Do you know a way to relearn the best for geometries instead of memorizing? Okay, I'm a chem major, so like the real reason's a little too complicated, honestly. So I would just go ahead and memorize. I think there's like 6 of them you really need to know. We're dealing with organic stuff. So you're never going to deal with d orbitals or f orbitals. So that limits it. I can make an announcement later and I can upload. This will be uploaded to Canvas Magic. What's this? What's this? What are we talking about? Possibly, if I figure it out. Yes, if I figure it out. Maybe one of you can email me and tell me the directions or something. I can do that. Okay. Anyway, let's do this. Go on. So now we have this question of like, where are these lone pair electrons residing? And that has to deal with the resonance argument. And maybe I should just jump to resonance now. I'm kind of leaning towards that. Yeah, I'm going to jump to the resonance stuff. So let's go to page 12, and we could always go back and do some of the more of this another time. So let's go to 12. So this is the other big ticket item for your first exam. So resonance is really big and hybridization is really big from chapter 1. So let's just kind of do those today. No, lone pairs are not drawn in, and they're not going to be drawn in for your first exam. They will be for the rest of your exams, and they will be for organic too. But there's a reason they're not in right now, and that's because they kind of give away like what you should do for resonance and stuff. So we don't have them on for this first test, if you see them. Anyway, so what you want to do is, and I just want to make a disclaimer real quick. There are a lot of different ways you can do resonance and there are a lot of different arrows you can do, and you're technically right. You are totally valid, and it's not that one is better than the one is right and one is wrong, but there is one that is better than the other, and I'm going to give you guys guidelines so that you guys always get like the same best structures, okay? And I hope that kind of made some sense. Do you know if they're going to give us the number of structures? Yes, we would. So there are going to be two different types of ways we would give it to you on the test. So we would give it to you in the sense of, we would say parenthesis with a number. So that means that there are two other structures or two other structures. This is just a theory question for you. But you can see over here, 2, 2, 3, so on, so on. Or we could say, let me give you this preview. Hold on. Or we could say something like this. So this is an applied question. And we're going to talk about this like next week. But you can see, for look at B, line B, there are two additional resonance structures for molecule E, wherein each structure only has one atom with a formal charge. Yeah, that might sound crazy to you right now. It's not going to sound crazy to you next week. But notice how we said one atom has a formal charge. There's only one specific way that you are going to do resonance arrows where you will get an atom with a single formal charge, if that makes sense. So we kind of encrypt it in the directions some way so that you'll know how many to draw. But you'll definitely know how many to draw. Okay. So here are my rules, okay? So maybe this is another thing for separate paper. Let's do this. So resonance rules. 1, okay, 1 move at a time unless exceed octet. Okay, so I know these make no sense to you right now, and that's the point. They make no sense now, but they'll make sense to you after I do an example. 1 move at a time unless you exceed the octet. 2, always source to sink. Okay, and I know you don't know what that is yet. Always source to sink, okay? Some sort of source to some sort of sink. What the hell does that mean? Okay, and then 3, okay, after that is when given the choice, so when given the choice, in cyclic systems, this one's a long one, in cyclic systems, okay, so that means a ring as opposed to like a line like this. So this would be cyclic, this would be linear, okay? So when given the choice in cyclic systems, go pi bond to lone pair, not pi bond to pi bond. Okay, those are literally the 3 main rules that I need to give you, and then you'll get it right every time. Okay, I know that seems crazy. Okay, so 1 move at a time unless you exceed the octet, always a source to a sink, and when given the choice in cyclic systems, go pi bond to lone pair, not pi bond to pi bond. All right, I'll catch you in a sec. So, and a very, very good, another, I guess this isn't really a rule, I'll put as a star, like when you see a carbonyl, which is what really just looks like this, something like that, that carbon-oxygen double bond, R just means the rest of the molecule. The carbon-oxygen double bond, this is a very characteristic first step. So I'll just say maybe that's like the first step, okay? That's just a good tip for you, okay? That's a very good first step, is to push those pi electrons out. All right, everybody good with these rules? I know they don't make sense yet, but they will make sense soon. Okay, I got 4 minutes left, so I'm gonna try and do a couple problems. All right, so notice how in this example, source to sink, okay? We don't know what that is yet, but we see that carbonyl, and I drew that arrow going up, okay? That's a very characteristic first move. Just accept it for now, okay? And then it looks like I go in this next one from a source. So a source is a lone pair or a pi bond, okay? A source is always a lone pair or a pi bond. So that's just some source of electrons, okay? And then goes into some sort of sink or a deficiency, something that doesn't have electrons. So a positive charge means I don't have a lot of electrons. But a negative charge, because electrons are negatively charged, means that you have a lot of electrons there. Okay, so it's 1 move at a time, okay? And from source to sink, and when you see that carbonyl, you typically start with that, okay? And we'll talk about major contributor in a second. So let's just start with these structures. So if we look at A, we see we have 2 structures we want to draw. I see that carbonyl. Okay, so that carbonyl, you know, I knew that rule. Stephen told me that. Let's push those pi electrons out, and let's kind of form this structure. Okay, so whenever you take electrons away from something, it becomes deficient or positively charged. When you put electrons onto something, they become electron rich or negatively charged, okay? So this would be the first structure, okay? And then we need to do source to sink, okay? So a source of electrons, either a lone pair or a pi bond, to that sink or to that deficiency. Well, I didn't touch these lone pairs yet. Let me push those in. And the resulting structure is that. Okay, and that's it. So that's so far how you do resonance. And you only get better with this with practice, honestly. There's no like way I can get it better for you unless you do more practice. Let's keep going. So for 2, I see that I have, this carbonyl, so let me start there. Okay, that's a very good first step. Okay, and there are these lone pair electrons there. Okay, and what happens is that these electrons are going to push in, like source to sink, like that. So we get, so a source, again, lone pair or pi bond into that sink. Okay, and I'm really good at these formal charges, knowing where they go, plus, minus, stuff like that, and you will get better at it too. There is a formula. I hate the formula. I feel like you can just like look at them and know. But the formula for it is formal charge equals valence electrons minus dots minus sticks. So here we have 6 valence electrons for sulfur, minus dots, so minus 2, so that's 4, minus sticks, minus 3 total sticks, so that's positive 1. Okay, that's how I got that. So you can do that, it's a slower method, but you'll get faster at just seeing like, oh, I took electrons away, positive. I put electrons on it, negative. Like that's how I did it. All right, what's going on with C? Question mark, hint, any electrons capable of being delocalized? No, I don't see a way that I can push these in here and push something out. And the reason that is there's an imaginary hydrogen here. And how many electrons are at this carbon? Well, there's 2, 4, 6, 8 electrons. So you are at the octet configuration. You cannot push any more electrons in. Okay? So no, there are none. So just know that. So how do we know? And I think we just got what I was going to say. Yeah, there are no pi bonds. Exactly. I was going to say that. So this comment is perfect. There are no pi bonds. So that is what we look for in resonance. We look for some sort of source of electrons, so a negative charge, and then there has to be a pi bond or either in the form of a double bond or a triple bond nearby. Okay. So notice how there wasn't that there, but it is here. It is here. It is here. That's very characteristic of systems with resonance. Okay. I'm going to do one more with you. I'm going to do a ring, and then I think we're going to have no more time for today. If that's okay. So let's do this one for F. Okay. So for F, I don't necessarily know where to start, but typically a good source would be my lone pairs, okay? And this is why, and for consistency purposes on the test, Dr. Peterson would say, or Dr. Habenick, whoever you have, would say, the draw resonance structures where there's one formal charge only on each structure, So that would give everybody a way to get structures that like was consistent, okay? But if I chose to start here, I would basically push these electrons in, okay? But I exceeded the octet at this configuration. Okay, there's 2, 4, 6, 8 electrons there. And one of my rules earlier was do one move at a time unless you exceed the octet. Well, if I exceeded the octet, I have to push these electrons out, okay? And then that also follows my next rule. In cyclic systems, when given the choice, go pi bond to lone pair, not pi bond to pi bond. So that means pi bond to a lone pair, not pi bond to a swivel to a pi bond. So that may not be obvious, and I can draw that here. So what pi bond to pi bond looks like would be that. What pi bond to lone pair looks like would be that. Okay? We want to do this one. We don't want to do that one. If you do this one, you end up skipping a lot of structures. You skip a lot of contributors. If you do this way, pi bond and lone pair, you don't. Okay? And this is just from years of teaching this, like I've kind of found out how to like catch all of those issues. So the resulting structure from this would be so we're here. Okay? Let's keep going around the ring. So let's push this source in. And then remember, pi bond to lone pair is the best thing. Okay, and then there's one more structure. We can push these in over here. And we get, okay. And I think that's, yeah, that way I definitely went 2 minutes over. So on Monday, we're gonna finish up the chapter 1 material and we'll do more resonance. I know we need to do a little bit more practice on that. We'll talk about major contributors. But yeah, so this is pretty much how office hours are always gonna work for me on Mondays and Wednesdays. I follow along with the student workbook. I'll make sure I know where you guys are in class, and you guys can feel free to like email me whenever. I'm obviously here to help you. Like I really want to help you guys. I love this stuff. I want you guys to love it too. Like people are always so scared of this class and they think it's so tough, and the truest like reality is that like it's no harder than any other class as long as you learn it right. So put in the extra effort, come to office hours, and you guys will be so happy when you take your MCATs or DATs and you guys rock the orgo section. Okay, that's it, and I will see you guys next week on Monday.
Thank you.
Yeah.
Thank you.
Thank you.
Thanks.
Yeah.
Thank you.
Wait, Steven, I have a question.
Sure, that's Emily. I know that voice.
Yeah. So should we just keep working in the workbook, and where do we correct our answers?
Yeah, so you can, what you should do is like what we did today, like any of those problems that we didn't touch, like, you know, like there's some of these resonance ones or some of those hybridization questions that we didn't do, or these classifications, finish all of those. But also on Canvas is like the answer keys to all of this. So you can just like go and check them after you do them. Mhm.
Okay, I'm with the other professor, and I couldn't find your Zoom link. With
Okay. Yeah, I'll reach out to Dr. Peterson and have her like forward that to Happiness Kids.
All right, thank you so much. Bye,
Yeah.
Steven.
See ya. Anybody else have any questions before they go? All right, see you guys.